Hello and welcome back. So this is my UART development circuit. It's got basic transmit facilities, which means it's just looping round and sending out the same sequence of 16 characters that are in a row in the ASCII table from this counter chip. I can also make it receive a character and it will output it here. What I'd like to do today is move this circuit towards something I can actually interface back to a CPU, make it useful. Going to need a bit of extra circuit space for that. Now there are a few flaws in this circuit as it stands, and the first is in this receive circuit. So I've just fired up my Larson scanner code, which is just sending the serial codes down the line to create the familiar Knight Rider pattern, and that visually looks fine. But I'm going to take the delay out of it now, and that seems to fill up the entire display in a blur because it's running really quick. We kind of expect that, but I'm going to just try and light up one LED now. So in theory, just this light here should be lit up, and it does look slightly brighter. The reason why all of these are lit up, because this is just raw output from the shift register. It gets loaded initially into this position, and then as it streams additional bits in, it moves along. And then because there's no delay in the circuit anymore, it's pretty much straight away moving on to the next one. So what we need to do is modify the circuit so it can actually store the completed byte. And then we've got it somewhere where we can consider actually using it to hand over to a processor. Now, traditionally, when we've said we want to store something, we use the 574 latch chip. I also managed to get hold of some of these 8 LED bar graph displays, which I would dearly have liked to have got hold of earlier in the build, because they're going to save these 2 wasted spaces. Right, so instead of driving LEDs directly, I've taken these to the inputs of the latch chip, and then I'm going to take the outputs over to the LEDs. Let's not forget power and ground. Right, there's an output enable down here. This is one of those circuits where we could just use the 574 and then we could selectively drive the output to wherever it's going to end up going. But in this case, I'm going to have it permanently outputting so we can display it on the LEDs, and then we'll have a separate driver taking it out to what will probably be some kind of data bus. Okay, so now we've got some kind of a load signal here. Okay, so if I send a character, I can get the data to load, but we need to do that automatically. Now we want it to go high because it's the rising edge that will trigger the load here. That's not right, so that must be the one that goes low. Awesome, now that looks like it's doing exactly the same thing as before, but the value is being held in here. So now if I run the code that is very rapidly sending the value 1, it constantly says the value of 1 here, and it's not sliding the value along and blurring the result. That's awesome. Right, now I want to take this 193 chip out. I'm not going to want that anymore. This is just a test counter. I need a reminder of where all these lines are at. I'm going to use a resistor array to tie them all to ground. That was the clock line. Don't need that anymore. So from the 193, that's going to be bit 0. Then this will be bit 1. This one will be bit 2. That'll be bit 3. That is bit 4. And it's this one. Okay, move that to the top, be slightly less tight. Okay, so we've got the output bits stably held in the latch, but we need to be able to push it onto a data bus on demand. And for that, I think we'll use a 541 line driver. Right, so we've got two output enable lines. Let's take one of them low permanently. The other one is going to be our output enable. I'm actually thinking it might be easier if I line that up with it down here. So now I need to bring these 8 wires up to the inputs to this. Okay, so now I need to show you this circuit. Now this is a kind of CPU bus test circuit that I've been building. It's basically designed to provide the kind of signals that I can generate from a CPU without needing to try and make space for this next to the CPU while we're developing it. So what we've got is a bus display. We've got a set of dip switches that can output a value onto the bus. If I select it here, let's get some power in here. If I tell the contents of the dip switches to assert onto the bus, they get displayed. Or more importantly, if we cross-connect ground with this circuit and plug this into the bus lines, then whatever we have on here should be output onto the bus. Okay, that's nice. And of course, what I've shown up here is that these lines up the top are intended to be a connection to the bus. So what we can do is bring all of these lines across to there. Okay, so now this circuit is constantly sending whatever is on the bus. So every time it's finished the bit cycle, it will pull in the next value on the bus and send it. Of course, that's not what we want, but it is a start. Okay, so right now we've got 32 selected, so we're getting lots of spaces. We can start scrolling up through the alphabet if we want. Let's fix that in a bit. So now what we need to do is we need to work out how to control this load line such that we only actually load the data when we've got a value on the bus we want to send. This is an interesting circuit. Whatever character it's received last, it will feed back out. But only while I'm holding this button down, which is going to be the assert to bus for the received byte of data. So let's assume this button here is going to be a load value for the UART send functionality. So when that signal goes low, we want to pull in the byte of data on the bus and send it. Okay, let's have a look at how to do that. Okay, so let's start with a quick reminder of how bus operations happen on my CPU. So we've got the clock cycle here, and a data move operation starts with an assert to bus. So whatever is providing the value will push its data onto the main bus. So at some point in the first half of the cycle, that will become valid on the bus. And then the actual read needs to happen in the second half of the cycle. Now the load line goes low for the first half, and then it returns to high. Conceptually, most of the time we talk about this rising edge as being at the point where we expect the load to happen. So we're expecting the transmit to happen as the result of a load operation. So the load line will look like this within the cycle, but the transmit circuit we've built, that's going to load while the data's actually there. So this is what the load line would actually want to look like. And this carries a pretty big assumption that there's some kind of synchronization between the clock on the CPU and the clock that's driving the UART. And that's highly unlikely to happen unless we go out of our way to do it. And that seems like a crazy constraint to have. So what we actually want to do is get the load to happen in this segment here. So we don't know if the clock circuit in the CPU is going to be running at high speed or is indeed me pushing the clock tick button. So we really want to just generate a low going signal as soon after the rising edge on the load line as possible to support high clock rate, but we want this to be no bigger than we actually need it to be. So this is why what we want is an edge trigger circuit. Now, the problem is there's no static circuit that can actually generate this edge signal from the input. We need a circuit that takes time into account. And the way we do that is we look at this byproduct of our logic gates that they are not instantaneous, and so we delay the load line. Now in this case I'm going to delay it using an inverter, so what we get is the opposite of the load line. So conceptually the inverted copy of the load line should be the exact complement of the original line, but it will actually have this delay on it because the inverter has a time cost. And now we can look at this strange property where the inverted line and the load line are both high for a brief amount of time, which roughly coincides with the rising edge. So if we build a circuit for that, this is what we get. I want a low going output, so I'm using a NAND gate rather than an AND gate. But this will mean that we get a low output when the load line and the delayed load are both high. So we get this downward going pulse, and the length of this pulse will be exactly the delay we've got on this inverted input. Now that may be very, very small, so we could stick some additional inverters on in order to lengthen this pulse. Okay, so this is a 74LS04, and that's going to be used to create the delay. It's got 6 inverters. Now we want the result to be inverted, so best use an odd number of them. I'm going to power this completely from this serial device. Actually, you need a 5-volt line over here. Okay, some of these pins are really loose in these holes. I'm really not very confident they're making a good connection. I just want to check the voltage level at the top here. Okay, 4.15 volts, that's not great. 4.59, that's a bit better. That's a little bit better, hopefully stable. So our main UART circuit is 3 breadboards plus this test board, so it's not going to be too bad. So I want to take one of these outputs. So this button is going to be transmit. So I'll take whatever is on the bus and transmit it. That's the hope. Also need a NAND gate. I've got one spare inverter, so I could use an AND gate here if I needed to. But I think we're going to have a use for the other NAND gates. There's some spare ones down here as well, but I think we need them all. So this is the input to the first inverter and also the first input to one of our NANDs. Okay, I want to fire up the scope and start having a look at this. Right, yellow trace, I'm going to make the button I've got down here. And purple trace is the output of the last inverter in the chain, so it's the 5th one. A rising edge trigger, which is going to be when I release the button. Okay, we're zoomed quite in, so nothing's very sharp, but that purple trace does look like it drops after the yellow trace rises. So now we need to feed that output into the second input in this NAND gate. Let's take a look at the output of that. That actually looks good. Okay, so that is our rising edge detected successfully. Now what I want to do is feed that output into a set reset latch. Okay, so let's feed the output there into first input of that NAND gate. Now we need to cross-connect the outputs. I am very aware that I've been making a lot of set reset latches of late, but they are very useful. So that's the output of the second one, goes to the second input of the first. And then the output of the first goes to the first input of the second. Now let's have a think about this. The load signal on here is currently controlled by the carry of this counter. I actually think that that carry is going to be the second input over there. So we set the set reset latch on the detected edge and then we clear it when the counter hits the carry. We're still counting 16 at the moment, but I'll change it at some point. Right, we won't need this. Right, so we want to load the data off the bus and we want to do it when we trigger a send. So we could use the detected edge, but that's potentially going to be very short. But we could actually use this output from the set reset latch, as that's going to be low for a minimum of the stop bit and potentially all of the interval between send. No, it's active low, so we want it off that one. But the active high, we're going to take it to the clear input. Okay, let's see what that gets us. That looks a lot like the signal. Aha! There we go. So I should be able to change these dip switches and get a different character out. Because what this signal is doing is it's acting as a control signal to send whatever data is on the bus. So I could take this switches away from the bus, push this button, which takes the current receive buffer and puts that on the bus, and send that back. So that's currently a space. But if I go back to my keyboard, press A, send that, that's great. Okay, so that is the transmit section in a position where we could presumably use it directly in the processor. But we would have to be careful that we didn't try and send bytes more frequently than the serial port is capable of doing. So we've got lines for send and asserting the receive back to the bus. That's most of what we need. The only thing we're really missing is some control information, because our processor needs to know if there's a byte being received, and I think it could also do with knowing if there is a byte currently in the processor being sent. Now in the case of send, that data is up here. Okay, I don't know how obvious it is, but that LED comes on for a tiny amount. So now we need to work out when the receive circuit has got a byte. And once again, I'm going to use a set reset latch. Final output back to the second input. Do the same up there. Turn the scope off. Right, so what we want is we want to reset it when we read the byte. So let's just grab that assert line, and then we want to set it when we have a byte. So we have a new byte when we fire this latch line. So we should just be able to hook into that. So be one of the two outputs. Right, so let's try sending it a byte. So the LEDs come on, and we assert it to the bus, and it goes off. Great. Right, so now we've got one LED indicator says we're currently in the process of sending a byte, and therefore we wouldn't be able to send one, and one that a received byte is available. Now I've got a third control line here, and we're going to use that to assert the data back to the bus. Okay, so this is the main bus as far as we're concerned. Just need to work out how to get the data onto here. I think we need a bit of space. Right, so this is a 541. It has inputs at the bottom and outputs at the top. It could actually be easier if we put it in upside down. Around there. And we've got our 8 outputs. I've got an output enable here. We need to tie that low. I think it's going to be a lot easier to do that now. So then our inputs are arrayed along here. Line is going to be the assert to bus. That's interesting, these are all defaulting low. Now I only need 2 bits. I can bring 4 of them low with that. I think I might actually make one line high and one line low of these 2 bits that I'm not using. Just because if no lines are active, it will show us that we're actually doing something. If I send a character, our status bit is on, which I can read off the bus with this assert line. That's good. Okay, I think this circuit is complete for today now. We've got both send and receive, and then we've got this status output section, which will tell us when we've got a byte available or when we're in the middle of sending a byte. Now remember, this board at the bottom is just generating the simulated inputs equivalent to what the CPU is going to generate. So we've got that all on 3 breadboards, 2.5 really, and that is a functioning UART. Plenty of features we could add to it, but that is a minimum UART that we could interface to a CPU. And I think probably in the next video, that's what I'm going to do. Just bolt this into the CPU and actually use it, and then perhaps add some more features in the future. I think this needs a whole bunch more tidying up, but I don't have the time now to cut all of these wires, which none of them are particularly easy. So this button will send whatever is on the bus. If we receive a byte, it's displayed here, and we have our status byte. So we can see our status bits with asserting our status byte to the bus. And then we can read it off, which will clear the byte available bit. That's great. Okay, next video I'm going to interface this to the CPU, and so I don't know whether or not that will be in the UART series or the CPU series, but I'll kind of play that by ear. But I hope you found this interesting. Thanks a lot for watching, and I will see you again soon. Thanks. Goodbye.